Today, across every scientific and governmental discipline, the scale of global data generation is accelerating at an exponential rate. Making this information useful is frequently misread as the simple act of uploading a spreadsheet to a public website. However, the formal open definition establishes rigorous parameters. Data is only truly open if it is engineered for anyone to use, reuse, and redistribute without technical or legal barriers. When data is published in unstructured or proprietary formats, it creates digital friction, leaving valuable information isolated in silos that require specific paid software to access. This isolation results in a digital Tower of Babel, a landscape where vast datasets exist in the same space but cannot communicate or be combined. To solve this, open data functions as a technical and legal framework designed specifically to achieve absolute interoperability. Interoperability is the capacity for diverse digital systems to automatically compute, read, and combine distinct datasets without manual reconfiguration. This requires data to be non-personal, universally accessible, and stripped of any commercial restrictions that would prevent its use in any field of endeavor. Building a functional data commons involves navigating several architectural layers, from standardized publishing protocols to global repository networks. This matrix identifies where open data exists within the wider ecosystem. The open quadrant contains data that is openly exploitable and shareable. This strictly excludes private data. Instead, this space is reserved for the intersection of government records, scientific research, and domain-specific datasets. Moving raw data into this quadrant is a complex lifecycle that begins with acquisition and curation, followed by precise description and packaging. The goal of this process is to meet FAIR O standards, ensuring data is findable, making it accessible, keeping it interoperable, and reusable under open licenses. We can visualize these requirements as an openness protocol stack. It begins at the file format layer, where proprietary extensions are converted into open formats like JSON, XML, or CSV. Proprietary formats create software monopolies, forcing researchers to purchase tools. Open formats ensure data remains machine-readable and easy to migrate as technology evolves. The second layer adds vocabulary and metadata, providing the necessary context to describe exactly what the data represents. Without standardized vocabularies, datasets remain invisible to external search agents and cannot be discovered. The third layer establishes identity through a persistent identifier, or PID. This provides a unique, permanent digital address for the data package. These identifiers track different versions and distributions of a dataset as it is updated over time. PIDs also ensure the data can be cited accurately in academic literature, allowing other scientists to point back to the exact source. The final layer is an open license, typically using CC BY terms. This makes the license information machine-readable and removes legal ambiguity regarding reuse. This multi-layered protocol is the primary defense against data rot, ensuring that information remains accessible and useful long after its initial publication. Beyond the protocol stack, we look at the physical and digital infrastructure where data is stored. General institutional repositories provide hosting, but the ecosystem relies on specialized environments for complex research files. Domain-specific repositories, like HEP data for high-energy physics, are engineered to enforce the specific scientific standards of their disciplines. These repositories differ structurally based on the data they house. GIS databases require bathymetry support, while humanities archives like ARDA focus on surveys and polls. National governments manage a parallel infrastructure of open government data portals, providing a centralized point of access for municipal and federal records. Together, these highly specialized housing structures form the decentralized backbone of the global open ecosystem. Registries like DataSite serve as the organizational layer, tracking disparate repositories to make their content searchable. This registry data is crawled by specialized search engines to locate datasets. Dataset search utilizes schema.org markups to identify datasets based on metadata. Swoogle employs semantic web indexing to crawl the network and map relations between ontologies. This combination of registries and semantic engines bypasses the need for central governments, making the massive global network easily navigable for any user. This architecture provides an alternative to the traditional proprietary model of research. In a proprietary system, Restrictive copyrights and siloed formats create a scientific anti-commons, where discovery is hindered because the necessary data is fragmented and inaccessible. Adhering to open frameworks is the method for overcoming the anti-commons, linking disparate datasets into a unified, interoperable ecosystem. The impact of this framework is practical and immediate. Local governments use this data commons to optimize urban mobility and improve public services. Global initiatives, such as the Human Genome Project, relied on this infrastructure to share and combine genomic sequences to accelerate medical discovery. True open data is more than a passive archive for old research. It is an actively maintained, machine-readable infrastructure. This highly integrated architectural foundation is the absolute structural requirement for the next stage of large-scale computational research.